Hello, this is Guillermo Campitelli, and this video is about the hypothesis testing approach. And I'm going to show two approaches: the frequentist or the traditional null hypothesis significance testing approach, which is commonly known as NHST, and we are going to see a Bayesian approach with Bayes factors. Now, these approaches that I'm going to show are not the only ones within the hypothesis testing approach, and within the frequentist and the Bayesian there are a variety of approaches. So I'm going to show you one approach, one frequentist approach, one Bayesian approach, but bear in mind that there are other approaches within these main approaches. Okay, so let's start with the frequentist traditional approach. And this approach, we call it NHST, has a number of steps. It starts with obtaining a representative sample. Second step is to obtain a summary statistic or a number of statistics of interest. The third is to define a null hypothesis that typically that hypothesis is that the parameter of interest in the population, the value of that parameter is 0. We are going to see other possibilities as well. And the fourth step is to obtain a sampling distribution of the statistic of interest. The fifth step is to determine the p-value, that is the probability of obtaining the score that we obtain in the statistic, or a more extreme score, and I'm going to show later what more extreme means. If in the population the value of the parameter of interest is 0, and the sixth step is to make a binary decision, either to reject the null hypothesis or not to reject. And I'm not saying accept, I'm saying not reject on purpose, and I'm going to explain why I'm saying it this way later on. Okay, so let's start with, I'm going to show these 6 steps with a case study, and the case study is the same as what we've seen in previous videos. It's a sample of 300 participants, and the variables of interest are academic achievement and study hours. And so the statistic of interest will be the beta 1 parameter. So basically here is the model: study hours, costing academic achievement. Obviously there are also unknown variables, and the mathematical model is a linear model with beta 0 as the intercept and beta 1 as the slope. So basically beta 1 tells us what's the effect of study hours on academic achievement, and for this example we are going to ignore the other variable, teaching quality. Okay, so basically we've got statistics, the beta 1, which is what we are interested in. So we have to obtain the summary statistic in our sample. Okay, so the data, here there are 300 observations. That's the same graph that I showed in previous videos. We are only going to be interested here in study hours and academic achievement, and not on teaching quality. So the same data as before. Now the third step is new in comparison to the previous approaches, and it involves to develop a null hypothesis. So, and typically the null hypothesis is that the value of the parameter in the population is 0. So the null hypothesis would be that beta 1 equals 0 in the population. Now, there are possible alternative hypotheses. One is vague, that says beta 1 is different than 0. So it doesn't say whether it's higher or lower than 0. And then the two directional hypotheses, alternative hypotheses, either that beta 1 is greater than 0 or that beta 1 is lower than 0 in the population. Now, it is important to note that the null hypothesis shouldn't necessarily be 0. We can determine that we can establish beta 1 to be some other value, doesn't have to be 0. So that other value that we decide is the value that we want to test against. But typically, most of the time, most of the studies in psychology use 0 as the null hypothesis. So I'm going to use this in this explanation as well, but it is important to know that it's not necessarily the case. We can use other values as the null hypothesis. Okay, so the fourth step is to define a sampling distribution. Now, this is the same procedure to defining the sampling distribution in the frequentist parameter estimation approach, but there is an important difference. In the parameter estimation approach, we assume that the parameter value of the population is the one estimated with our sample. So if in our sample we obtain a beta 1 of 0.6, then we assume that in the population 0.6 is the actual value, and then we do a sampling distribution starting from that point. Now, in NHST, we assume that the parameter value of the population is 0, or the one, as I told you before, it doesn't have to be 0, but it could be another predetermined value. So if we chose that way, that a predetermined value that is not 0, well, in this case we do the same. We assume that the parameter value of the population is that predetermined value. But as I said before, the most popular value is 0. So if our hypothesis is that beta 1 is 0, then for the sampling distribution we assume that beta 1 equals 0. And then the sampling distribution could be a normal distribution, could be a binomial, depending on the situation. So in this case we typically use a normal distribution, but I'm going to explain at the end that we can use other distributions. Okay, so within the sampling distribution step, there are a number of steps as well. So basically, what we do is we start with and before I start with this explanation, let me warn you that that's not what statisticians do when they actually do this step, and that's not what software do. In fact, they do another method, and I'm going to explain later. But I want to explain this because this is the rationale underlying the NHST and the sampling distribution. Then, because statisticians found shortcuts, they do something different. But this is the rationale underlying the procedure. So I want to explain this, and it makes our understanding of the procedure much greater. Okay, so we start with a population of values of academic achievement and a population of values of study hours. And these population of values are unrelated. Okay, so then we obtain a random sample of 300 pairs of values, one from the academic achievement population and one from the study hours population. So we've obtained these 300 pairs of values randomly. And then now we've got this pair of 300 pairs of values, so we can obtain the beta 1 statistic in this sample of 300, and we record that beta 1. Now After doing that, we'll repeat that thousands of times, let's say 10,000 times, and so we obtain 10,000 samples of 300 pairs of values, and then we obtain the beta 1's statistic in those 10,000 samples. So now we've got 10,000 beta 1's, and we can create a histogram with those beta 1's and obtain the mean and the 2.5 and 97.5 percentiles of this distribution. So I show you here, I did that using the software R, and this is the distribution. So beta 1's, the mean of that distribution is the black vertical line, and is very, very close to zero. It's actually 0.0002, so that is very negligible, and so it is equivalent to having a beta of 0. And the 2.5 percentile is minus 0.159. The 97.5 percentile is 0.158, represented in the graph by the dotted lines. Okay, so this fifth step is to determine the p-value. And what's the p-value? The p-value is the probability of obtaining the score beta 1 that we obtain. And let me just tell that in our sample of 300 participants, the beta 1 we obtain, so the statistic of interest, is 0.648. Yes, so when we determine the p-value, what we do is to determine what's the probability of having this 0.648, which is the value we obtain in our sample. So this is the actual sample, not the sampling distributions that we did before. The actual sample, we obtain a sample of 300 participants, and we have study hour values, academic achievement values, and we run a linear model. We obtain the beta 1 statistic, and the value we obtain is 0.648. Okay, so the p-value tells us how probable it is to obtain this value. If in the population the beta 1 equals 0, so it could be that in the population the beta 1 is 0, like we assumed when we developed our sampling distribution, but then by chance in the sample we obtain a very high beta 1 value, and it could be the case that it came from a sample distribution where the null hypothesis was true. Okay, so the p-value is that. What's the probability of obtaining that value? Actually, that value or more extreme. And I'm going to explain what more extreme means. Okay, so more extreme, let's look at here in this case. In this distribution, obtaining the beta 1 value is a very small probability. So you can see that that value never appeared in the samples we actually obtain, and if we use a theoretical distribution rather than made by resampling like we did, the probability is a very, very, very small number. Okay, so when I said more extreme, it depends on the hypothesis. So let me show you this in the next slide. So if the alternative hypothesis was beta 1 is different than 0, so we didn't establish before the experiment whether we expected a higher beta 1 than 0 or a lower beta 1 than 0, then more extreme means values higher than 0.648 or lower than minus 0.648. Okay, so when we establish a non-directional hypothesis, alternative hypothesis, we have to look at the two tails of the distribution, to the right tail and to the left tail. So basically we have to look at this part of the distribution, so to the right of 0.648, and we have to look at to the left of minus 0.648. So we have to add those this probability here plus this probability there, and we determine how likely it is. Now, if the alternative hypothesis was directional, let's say greater than 0, then we look at values greater than 0.648, and we don't look at the left of the distribution. So what we want to know is whether this beta 1 of 0.648 in this sampling distribution that comes from a population where the beta 1 was 0, it's when the alternative hypothesis was non-directional, so we said just different than 0, we have to say we are looking at percentiles 2.5 and 97.5. Yes, so basically if this value is within this interval, then we do not reject the null hypothesis. But if this value is to the right of this line or to the left of this line, then we reject the null hypothesis. So in this case it's very much to the right, so we reject the null hypothesis. Now if the alternative hypothesis was that it would be a higher than 0, so it was a directional hypothesis, then we don't look to those values. We don't look to this tail. We look only at this tail. And the reason why we use 2.5 and 97.5 before is because we want to have 2.5% of the distribution to the left, and we look at 2.5% of the distribution to the right. So together we have 5% of the distribution. Now, because we are, if the alternative hypothesis is directional, then we don't look at this part of the distribution, so we want to look at the 5% to the right of the distribution. So basically the cutoff, it won't be this one, which is the 97.5 interval, it will be a bit to the left, that is the 95 percentile. So basically when we have a non-directional hypothesis, we look at those sides of the both sides of the distribution, and when we have a directional hypothesis, we only look at the side we predicted we would find the value of beta 1 in this case. Okay, so the sixth step is to make a decision, and the decision is binary. So given that in this case the p-value is lower than 0.05, so it's much lower than that, and we decide to reject the null hypothesis. So basically we decide that this value we obtain, it cannot possibly come from a population in which the null hypothesis is true. So basically in a population which beta 1 is actually 0. So in this case we reject. Now what happens if the p-value is 0.5 or higher? So what happens if the beta 1, instead of we obtain in the beta 1 we obtain in our sample, instead of being here, it's around there? Okay, so what we do is to not reject the null hypothesis, and as I explained or as I indicated before, I'm not saying accept the null hypothesis. That's because the procedure we use, it doesn't allow us to provide evidence in favor of the null hypothesis. So this procedure allows us to provide evidence against the null hypothesis, but not in favor of the null hypothesis. And this is one of the problems that I'm going to explain in a minute. So basically, we follow this procedure when we do NHST, but as I said before, the actual procedure uses a shortcut. It actually doesn't generate a distribution of beta 1s. It actually uses a t-test distribution. It calculates a t-score, and it uses a t-distribution as a sampling distribution. And this is convenient because we know the theoretical t-distribution. We don't have to do it by resampling. Like the beta 1, there is no theoretical beta 1 distribution, but there is a t distribution, so it is more convenient to use the t distribution. But the procedure I explained better captures the rationale of the NHST approach. That's why I explain it in detail. Okay, so problems. There are many problems with NHST, and one interesting paper, which is the pervasive problems, or a solution to the pervasive problems of p-values, by Eric Young Wagenmakers. That's a paper from 2007. It gives an idea of the problems with NHST, but these problems were they are not new. They were proposed or indicated even in the 1960s, but in the last 10 to 15 years, the voices of criticism to this NHST approach are increasing, and the American Association of Statistics is being now telling people that should be very cautious in using p-values. The American Psychological Association is proposing a different approach. So there are a lot of calls for doing something with the NHST approach. Now, some of the problems here I'm going to show you 3, but there are more. One of these is that a low p-value indicates that our result is unlikely under the null hypothesis, not that it is impossible under the null hypothesis. And you may think that, well, if the p-value is very small, well, obviously it's not impossible, but is it not enough that it is unlikely? Well, the problem here is that we never test the alternative hypothesis, because the alternative hypothesis may be even more unlikely than the null hypothesis. But we don't test it. We don't generate a distribution, a sampling distribution of the of the alternative hypothesis. We only generate a distribution of the null hypothesis. So we never know how likely is the value if the alternative hypothesis is true. So we generate a vague alternative hypothesis. We don't produce a sampling distribution. So that is a problem. Maybe it is unlikely under the null, but it would be even more unlikely under the alternative. So this is one problem. Another problem is the binary decision. A p-value of 0.05 leads to a different decision to that of a p-value of 0.049999 when the difference is minimal, and in most cases it would be meaningless. So why would we want to make a binary decision? Why don't we just report what's the evidence and we shouldn't make it a drastic binary decision there. The third one is that even if we obtain a very high p-value, like for example close to 1, we cannot accept the null hypothesis. And that's because the procedure I explain in detail. So basically, if we use a probability notation, what we typically want in order to say something about the null hypothesis, to provide evidence in favor of the null hypothesis, is what's the probability of the null hypothesis being true given the data Rk is background knowledge. But we can't get that with the NHST approach. So as I showed you before, we need to assume that the null hypothesis is true to generate the sampling distribution. So that's why we've got this given that the null hypothesis is true and background knowledge. So basically, NHST gives us what's the probability of the data or more extreme values to the one we obtain, given that the null hypothesis is true. So we are assuming when we obtain the p-value that the null hypothesis is true. So we cannot say anything about what is telling us the data about the null hypothesis. Okay? So these are problems of the NHST approach, and a lot of people are proposing solutions. Like Jeff Cumming, in a number of papers and books, proposed the new statistics. Basically, there is nothing new in statistics. He proposed a number of methods that were developed much earlier. But basically, the goal is to eliminate the binary decision of the NHST approach and to do parameter estimation. So as I explained in previous videos, to use just parameter estimation and to not do hypothesis testing. Another proposed solution is the model comparison approach that I explained in previous videos. And finally, Bayesian inference, which is what I'm going to explain in the next video.